All right, so here we are. We talked about proteins. Now we're going to talk about one kind of group of proteins known as enzymes. These are proteins that, well, carry out a catalytic function. Now, when it comes to catalysis, kinetics measure the rate of an enzyme catalyzed reaction. So basically, how fast does a reaction take place? The chemical mechanisms tell how the enzyme actually does the chemistry. So how the enzyme accelerates the rate, how the enzyme causes chemistry to occur, and how the enzyme lowers the free energy of the transition state. Enzymes use the same catalytic mechanism as non-mechanistic catalysts. Enzymes achieve higher catalytic rates because of active site structure. So what are the amino acids that compose that active site? Is a key part of the rate. What are some factors that contribute to enzyme catalysis? Well, the complete mechanism of just a few proteins are known in great detail, and they serve as really some great illustrations of how other mechanisms are known, or how other mechanisms take place. Now, several factors contribute to the enzyme catalysis. The four most common ones, or the four most important ones, are proximity and strain effects, so molecular level proximity, electrostatic effects, acid-base catalysis, and covalent catalysis. Now, when it comes to proximity and strain effects, the substrate may come into very close proximity to catalytic functional groups within the active site. The substrate may precisely orient to the catalytic group, and the formation of a strained ES, or enzyme substrate complex, is going to take place. This is going to encourage, basically, it's kind of inducing the substrate to contort itself to be in that transition state. Because if you think about a substrate, it's going from a substrate initial state to a final state, or a product state. And what bridges the gap between those two spaces is what's known as a transition state. And so what an enzyme is going to do is basically, it's not going to grab directly onto the substrate, but instead it's going to say, hey, I see substrate, you're similar to what I'm looking for, but you need to do this or that, so that that is ultimately closer to that transition. Now, it's the active site amino acid side chains that are actually doing that interaction with the substrate. So here's what we've got as an example. Let me switch to my pen. So this right here, well, that's a group that should look similar. That's a serine. And that serine is establishing a hydrogen bond with this green object in the middle, which is our substrate. Now, if you look elsewhere, you can see maybe here's an aspartic or glutamic acid. So I'm going to use a single letter code of E, because that's the identifier for glutamic acid. Then we've got a backbone hydrogen bond established with the N-termini of an amino acid. We've got a threonine right here. So we've got all these hydrogen bonds that are being formed either between the backbone of the polypeptide or different R groups. Now, next up are electrostatic effects. They contribute to enzyme catalysis. So electrostatic effects, recall that the strength of an electrostatic interaction is inversely related to the hydration of participating species. So water is largely going to be excluded from active sites. So a hydrophobic pocket in the enzyme allows electrostatic interaction between the enzyme and substrate. Interactions between the substrate and amino acid side chains, or interactions between the substrate and prosthetic groups, are bound at an active site, are going to stabilize that transition state. So what is water actually going to do within the active site? Is it going to be helpful? Is it going to be combative? Depends. So hydration shells, remember that's how basically water is going to form this basic shell around different things. Because if you remember, water is a polar molecule. You've got the partial positive charge, and then at the opposite end of it, you've got this partial negative charge. So one thing that water could do, or that these hydration shells could do, is they could increase the distance between charge centers and reduce electrostatic interactions. And so they could reduce electrostatic interactions. Now, if we look at this is a nice illustration of how charged amino acids could interact in the absence of water. Okay, opposite end of that spectrum. What about in the presence of water? Well, if you look here, we've got our water molecules, and what they're doing is those partial negative charges are basically attracted to the positive charge of that amino acid R group. Now, over here, where there's that negative charge, then the partial positive charges of those water molecules are attracted to that negative charge. In which case, the distance between those two charges in the presence of water is going to be, well, pretty significant. It's going to be at very least the size of water molecules, and basically 2 water molecules. But then all of a sudden you got this gap where other things could enter there. So that's one of the things that water can do. Now in this case right here, in this nice little illustration of the active site here of an enzyme, did we see any water molecules? No, we didn't. If you can imagine water molecules forming or either participating in hydrogen bonding, or in the case of this group or this group right here, you have charged entities that would basically be repelled from one another. So that exclusion of water is important. However, there are some instances where water is going to provide for those, or provide as a hydrogen bond acceptor or a hydrogen bond donor or something like that, and it's going to participate in the catalysis. Now, what are some other factors? Well, we've got acid-base catalysis. So in acid-base catalysis, think about this as you have these amino acid R groups, and let's think specifically about those that can act as proton donors and those that can act as proton acceptors. Now, which ones are some good donors? Well, those positively charged residues. So arginine, lysine, and I'm using these single letter codes. We didn't really go into those single letter codes, but I will, so I do not expect them of you, but I will show them to you: arginine, lysine, and histidine. These are all residues that can be positively charged. Okay, now proton acceptors, well, aspartic acid and glutamic acid. These are 2 negatively charged residues. So these are two groups of players that regularly contribute to acid-base catalysis. So what acid-base catalysis is pretty commonly going to utilize is a histidine residue. Why is that? Because histidine has a pKa that's close to the physiological pH. If we remember what that is, it's about 6. Well, you might find it as 6.0 or 6.10. So it's very close to the physiological pH, in which case that means you've got a mixture of the you've got a mixture of the positively charged form and the neutral form. So it can act as a base or an acid near that physiological pH. Other amino acids can catalyze product formation through indirect acid-base catalysis. An enzyme-bound base abstracts a proton from a molecule other than a substrate, which then acts as a nucleophile. Direct acid-base catalysis is an enzyme-bound base abstracts a proton directly from the substrate. Now, our last group of enzyme catalysis, or factors contributing to enzyme catalysis, that would be our covalent catalysis. Amino acid side chain groups act as nucleophiles, forming an unstable covalent bond to the substrate. Intermediates formed are then usually hydrolyzed by water, so that would be an instance where water would be basically brought into the active site of the enzyme. And this is going to be a 2-step reaction. Your common forms or your common amino acids that are used in covalent bonding would be serine residues and cysteines. And this example would be a serine or a cysteine protease. This is a class of enzymes that what they do is they break up proteins. They break peptide bonds. And these 2 classes include a serine or a cysteine within the active site. But if you think about other amino acids that are capable of, are similar to these, we've got threonine and tyrosine. So those are also groups that could be involved in covalent catalysis by acting as, as a nucleophile.